Hello, these are the examples that will be similar to the questions on test 4 and on assignment 14, part 3, the last part of that. So first, here's our diffraction grading question, where diffraction grading has 5,000 slits per centimeter and is illuminated normally by a 532 nanometer laser. What is the highest spectral order M that can be observed? So we are looking for M. I will rearrange our diffraction grading formula for M. And first, let's look at D. We need to know what this is. D is equal to 1 over the number of slits per meter, which is 1 over 5,000 times 100. We are given slits per centimeter, and because there are 100 centimeters in a meter, we will have 5,000 times 100 slits in a meter. And so D will then be equal to 1 over 500,000. So adding that to my formula on the left over here. Now, this is the highest spectral order. So we will maximize the angle here, sine, to give us the largest answer possible. The largest value of the sine of theta is 1, and that's given to us at 90 degrees. Lastly, our wavelength. We just punch in 532 times 10 to the negative 9 for nanometers. And putting this in my calculator, I get 3.759 as my M. Decimal keeps going, but I rounded it off to here. And so the highest spectral order M that we reached was 3. We did not get to 4, and you do not round up to 4. Remember, M can be equal to 1, 2, 3, 4. It can only be whole numbers. And we did not reach 4, so the highest one we actually reached was 3. So that was our answer for this question here. For the second one, how thick minimum should an air layer be between two flat glass surfaces if the glass is to appear bright when a 600 nanometer light is incident normally? And then the second half is, what if it is to appear dark? So I will do bright in red, dark in green. So for bright, we use this formula. For dark, this one. So we are finding how thick it should be. So we're looking for T. So I will rearrange this for T. And we are looking for the minimum. So we're going to minimize M here. Let's try plugging in 0, the minimum value here, and see what we get for 600 nanometers. So that gives us something. I got 150 nanometers. So that was for the first part. And for the second part, same idea. Let's try plugging in 0, see what we get. We get a thickness of 0, which is the trivial solution. Of course, if you didn't have any glass there, the light would illuminate whatever the surface is, of course. So this is a trivial solution. Not what we are looking for. So instead, we're going to take the next lowest possible m, which is just 1. And I guess what I should have wrote here was 600 nanometers, not just 600. This gives us a thickness of 300 nanometers. So those were the answers for this question here. The important part here was to not put 0 for m and to instead not take the trivial solution and find the real one instead. So the third question here about interferometry. In a Michelson interferometer, light of wavelength 520 nanometers is used. The movable mirror is shifted by 0.095 millimeters. How many bright fringes are observed during this motion? So bright fringes are n. So I will rearrange this formula and plug in my numbers here. And I get 365.4. So we get 365 and a little bit of a fringe. So that was the Michelson interferometer question there. Polarization. Now this is just the first one of the polarization questions. I'm going to shrink these two down a little bit. They're a little big. So 3 ideal polarizing sheets are arranged in parallel planes. The second sheet has its transmission axis oriented 40 degrees relative to the first sheet. The third sheet has its transmission axis oriented 85 degrees relative to the first sheet again. So these are both relative to the first sheet. Unpolarized light is incident on the first polarizer. What percentage of the original light intensity emerges from the third polarizer? Okay, so first, let's find how much light passes through the first one. And it's exactly half, just straight from the formula. Now I2, how much light comes from this? So, and remember, we want this in terms of the original light. So I'm going to substitute in for I1 here, 1/2 I0, or I0, whatever you want to call it. And now I take my 40 degrees, because this second sheet is tilted 45 degrees relative to the first sheet. So cosine squared of 40 I get a long decimal. All right. And I will deal with that shortly. So this is the amount of light coming through the second polarizer. The third, I'll add some dashed lines just to separate a little bit. The third is going to be equal to the amount of light coming through the second one multiplied by the cosine squared of the angle between these two. So this is going to be I2. I'm going to sub in what we got for I2 in terms of the original light. Times the cosine squared of the angle between the third and the second polarizer. So here we're not using 85 degrees. We are told that both of these polarizers are at different angles relative to the first sheet. This angle theta in the formula is the angle between the polarized light and the transmission axis of the filter. So we know that the light coming through the second one will be polarized at 40 degrees relative to the first sheet. And because this one's 85 degrees off relative to the first sheet, there will be a 45 degree offset. So we have 85 minus 40 equals 45 degrees. And that is what we are plugging into our formula here. So from all of this, we get 1/2 I naught times 0.586824088, and the cosine squared of 45 is actually just 1/2. So multiplying everything together, I get 0.5 times 0.586824088 times 1/2 gives me 0.1467. I'll round it off there. I naught. Okay, great. So now we have the amount of light leaving the third polarizer in terms of the original light, and we are asked for the percentage of the original light intensity emerges from the third polarizer. What we do is we look at just this decimal out front here. So therefore, it is 14.67%. I just took 0.1467 multiplied by 100%, and that is our answer here, 14.67%. Last question, number 5 here. It's about the Brewster angle. A beam of unpolarized light in air travels into some acrylic plastic with an index of refraction of 1.49. So I'm going to say it starts in air with an index refraction of 1, and it travels into some acrylic plastic where it's 1.49. Has an angle of incidence of 60 degrees. Now it asks, will the light be fully polarized or only partially polarized? Well, let's go ahead and calculate what our polarization angle is first, and then move from there. So our polarization angle formula rearranged is going to be the arctangent of N2 over N1, which is equal to the arctangent of 1.49, which should give us an angle of 56.7. Punching in my calculator just to be sure, I am actually getting 56.13 degrees. So my memory was off. And that is my polarization angle. So, therefore, it will be only partially polarized. This is because to be fully polarized, the angle of incidence must be exactly equal to the angle of polarization. All right, so that was everything for this. If you have any questions, please ask me in class or email me. Thanks.